This project's goal was the development of a self-driving vehicle software based on the direct perception principle. The direct perception principle uses a simplified intermediate information space compared to other driving control approaches. It only uses the distance to the lane markings with respect to the car axis, the distance to the preceding cars, as well as the angle between the axis of the car and the road as its input space. The software is made up out of 3 different components. The RWTH component interfaces with the Open Racing Car Simulator, TORX, which is used as the driving environment. An affordance component generates affordance vectors, which are then used by a control agent to steer the car. The communication between all of the components is facilitated via ROS connections. The RWTH component interfaces with TORX via shared memory. The affordance component gets the vision feed from the TORX environment as its input and outputs an affordance vector for each time step. The affordance component is wrapped around one of 3 neural networks: an AlexNet derivative, a ResNet derivative, and a squeeze and excitation network derivative. Changing which network is used is as simple as changing one line of code. AlexNet small is an AlexNet derivative using a small input size of 64 × 64 pixels compared to the original architecture. The network is altered so that the receptive field is equivalent to that of the original architecture. ResNet small is a ResNet derivative that is considerably more complicated compared to AlexNet. Changes to the original architectures are the small input size, as well as the use of the switch activation function over the rectified linear unit. SENet small is the derivative of the squeeze and excitation network, which in turn reuses large parts of the ResNet architecture. It adds a squeeze and excitation block to each ResNet block to explicitly model inter-channel dependencies. It also uses depthwise separable convolutions instead of fully connected convolutions. This drastically improves parameter efficiency at the cost of a more complicated computation graph. The generated Python code, for example, is very long at almost 60,000 lines of code, almost 100 times longer than that of AlexNet's generated file. The agent component contains the reinforcement agent, a reward function modeled with imodel, as well as a preprocessing subcomponent that combines the speed input from the TORX environment with the affordance vector from the affordance component. One constraint of the TORX environment is that the reinforcement training has to happen in real time. For this reason, a simple 2-layer feed-forward architecture was chosen for the reinforcement agent. There are 2 ways to generate a reward function for the reinforcement training, either by computing it based on the game state in the TORX environment itself and sending it via a ROS connection, or by computing it based on the predicted affordance vector. In the case of the latter, the model code shown here is used. There's a separate training script for each affordance network. To train AlexNet, for example, run the training script train AlexNet that is located in the scripts folder from the root directory. The training script will generate the Python code from the model files and start training the network. To start the training of the reinforcement agent, execute the train agent script located in the scripts folder from the root directory. It will automatically launch the ROS master, the TORX environment, and the affordance component, after which it will start training the agent. The game output is set to 64 × 64 pixels. This makes judging the process of the training hard. To help with this, run the Python file vision listener located in the directory auxiliary/debugging agent. This script upscales the video stream from the TORX ROS environment by a factor of 10 in each dimension. The video stream is a little bit choppy though, due to the 5 Hz update rate of the environment.